Okay, so I formally welcome everyone who are joining this special set of DCS seminars. This is a two-part talk by one of the leading exponents of understanding polaritonic chemistry, Professor Wei Xiong, from the Department of Chemistry and Biochemistry at University of California, San Diego. So I formally welcome you, Wei, to the department seminar. I have Professor Deepa Kushalani, who is the chair of the department and had formally sent the invitation. Deepa, if you can just say hello. Maybe unmute. Deepa, could you unmute? Yeah. Yes.
Yeah, sorry, apologies for that. Good morning, everyone, and actually good evening, Professor Zhang. I know it's late on a Sunday evening for you, and I want to give you a very warm welcome from TIFR. Thank you for agreeing for these two online presentations. These are going to be a fantastic set of presentations, and we have a wide array of students and members of other universities as well and other institutes in India who are participating as the audience members of this. And just from TIFR perspective, I'll just introduce you a bit to our department. We are Department of Chemical Sciences at TIFR, Tata Institute of Fundamental Research. It's an institute that basically deals with research and education of the STEM subjects. We're looking at biology, chemistry, physics, maths, computer science. I don't want to take too much time for your talk, but suffice it to say, we hope the next time we do this, it will be in person. As much as COVID was a negative thing, it sort of evolved these online interactions into a more efficient way of doing things. However, I do think there are many things that are missing, and personal interactions go a long way. And I hope sincerely that you will make the effort, and we will definitely be able to host you here, and would love to do that in future. But in the absence of that, I'm going to pass it back to Jyotishman, who's going to introduce you. And again, a warm welcome, and thank you so much for doing this.
Thank you.
Thank you. Thank you, Deepa. So let's start the set of talks, what we are all here for. So just a short introduction to Wei, and I'll do this tomorrow as well, but I just wanted to introduce to the audience here. Wei did his bachelor's from Peking University in 2006 and then moved to Professor Martin Zanni's group in University of Wisconsin-Madison, where he got introduced to two-dimensional IR spectroscopy. He finished his PhD in 2011, did very well in Marty's group, then moved on to his postdoc position at University of Colorado Boulder, where he was developing soft X-ray techniques as well as looking at shocks, how shocks propagate in nanoplasma. So there's something very similar to that happens in TIFR as well with the high intense laser physics group in TIFR as well. So where there will be common interest when you visit us at TIFR. Wei then moved on to UCSD in 2014, where he joined as an assistant professor, finished his tenure by 2020, now is a full professor at UCSD. He is basically the Ken Wilson Faculty Scholar. Wei has expansive research group in applications of nonlinear spectroscopy, setting up 2D IR spectroscopy in his own lab, but also went on to set up vibrational sum frequency generation techniques to probe biology. And of very intense interest has been his understanding of the so-called polaritonic chemistry that has emerged in the last 12 years. And so Wei has been one of the leading exponents of trying to parse out the details and understand what is real and what is how we can explain what we see as real phenomena in these photonic cavities. So he kindly agreed to us to visit, of course, TIFR. However, the visit was imminently not possible at that time, but he has given his time for a two-part talk today. The first talk will be tutorial. This would be introduction to the concept of light matter strong coupling. And the second part of which will be tomorrow at 9:30 a.m. exactly the same time to join us, where Wei will be talking about his latest research from his lab, demonstrating how to understand polyatomic chemistry. So Wei has won a lot of awards, phenomenal 10 years he had spent, 10 to 11 years. He's been, of course, the DARPA Young Faculty. He's won the DARPA Young Faculty Award, the DARPA Directors Fellowship. He was one of the finalists of the Blatnick National Awards for Young Scientists. He is also the fellow of the American Association of Advancement of Sciences. And very recently, he was a National Brown Investigator. He won the National Brown Investigator Award. And there are many more to come. He is helping the community understand this very interesting scientific topic. So, Wei, I welcome you. The floor is all yours.
Thank you, Jadishman. Thank you, Deepa, for your warm welcome. And it is really a great opportunity for me to meet my colleagues at TRFR as well as broadly the India scientific community. And I definitely look forward to in-person visit at some time, hopefully in the near future. So as what Jadishman mentioned about, what I will try to give today and tomorrow is going to be a series of two talks on our path towards rational understanding of polariton chemistry. Specifically, for today, I will focus on the fundamentals and tutorial and give you a little bit flavor on what we could do. And then tomorrow, I'll focus on the latest and greatest. So, see if I can advance the slide. All right. So, as chemists, most of I believe our audience would be chemists, that when we learn chemistry, we know about thermal chemistry. We heat up things and we change it. And that was what we as human beings has been doing it for, 10,000 years, or if it's not longer, as soon as we learn how to use heat and fire. But that's not sufficient, right? If or efficient, because you pretty much elevate the temperature and you just let everything that's above that temperature, above the certain energy to happen. So it's not selective. And then in the past, many decades, as chemists, we have been thinking about other way of doing more efficient and selective chemistry. One of the example would be electrochemistry, where we use electrode to actually apply potential and pass electron from the electrode to the reactants and then trigger certain reactions that already have become still a very, very, a hot topic now in the community and a more mature topic compared to the topic we talk about. And it's more efficient already. And then nature has taught us that there's another way to do chemistry, that is by photochemistry. That means that if we can have a dye or chromophore can absorb either visible light or UV light or any kind of color of light to promote the electron from the valence band to the conduction band, or the HOMO to the LUMO, then those excited electron could also trigger chemistry. Because we have a lot of solar energy, so that is also very energy efficient. So those are all the traditional way that could already be included in the chemistry textbook. What we are going to talk about is a new emerging phenomenon that is, I guess, trying to get its way into the textbook, hopefully in decades or a few decades. That is the so-called polariton chemistry. So I will go through it in a very detail for the rest of the talk, but pretty much this is a phenomenon that leverage the interaction between matter and quantize the photonic field that's usually created by a cavity structure. And people have shown, such as the group of Emerson group, who's the leader of this field, who initialized this concept of polariton chemistry, have shown that by taking, like for example, this type of chemical we call R, that can either undergo a silicon-carbon bond breaking or silicon-oxygen bond breaking. And when they put it inside of the cavity, basically a pair of parallel reflected optics, and they can show not only the reaction rate is slowed down compared to the one that outside of cavity. More importantly, that while outside of the cavity in normal condition, the reaction actually favor to break the silicon carbon bond. But when they put it inside of cavity, the reaction start to favor to break the silicon oxygen bond. So this is quite a phenomenon experiment because of it may provide a alternative way to control chemical selectivity. I see there's a hand.
I will take questions a little bit later, maybe. So
Okay.
you can continue. Sai,
Okay,
yeah,
thank you.
yeah.
And then, so Emerson's group by themselves have published many works. And then recently, a independent group, Blake Simpkins at the Naval Research Lab in the US, also studied a bimolecular reaction inside the cavity. What they showed is also conceptually, they can see that the reaction rate is slowed down. Especially as the vibration mode are strongly coupled to specific the cavity mode are coupled to specific vibrational mode, and they can see that. So it seems like there has this really exotic phenomena has been actually proved and reproduced by different groups. And there's many other groups actually have shown this result. So um, however, so that's really amazing phenomenon lead to a fundamental question, which I would refer as a the type of million dollar questions. So first of all is what is the mechanism behind this proton chemistry? And more importantly, that can we actually have a guiding principle so that if my organic colleagues comes in that bring me a set of reaction, ask me, hey, Wei, what type of cavity you can design to either slow it down or accelerate or do whatever. Do we have a principle that I would say that based on the best of my understanding, the community do not have such a guiding principle. And that is what we're trying to chase after and try to understand. To basically really try to help the community to move from empirical and trial and error type of attempt into a principle guided efforts. So for today's talk, that I will focus on introducing the fundamentals of protons and also its dynamics. Specifically, I'll talk about three areas. First are the fundamental basic principles of strong coupling in the including cavity formation as well as single particle strong coupling limit and collective strong coupling limit. And then I will move on to talk about mostly infrared characterization, including linear infrared characterization as well as two-dimensional infrared characterization. This will be the big part of the talk. This is the main tool that we use to study proton dynamics, and it's also I hope to convince you this is the strength of the technique to help us to deconvolute a lot of the complicated dynamics inside of the cavity. And lastly, that I want to just show you one example what we could do using this technique to disentangle what proton can do and cannot do. So first, let me introduce you the fundamental concept about strong coupling. So to talk about strong coupling specifically, we are talking about coupling between matter and the photonic resonance. So then the first question as a chemist when I first entered this field was, what is actually a photonic resonance? So let's go back to think about what is a atomic resonance. So from the very old classical picture, we think about resonance as electron orbit around nuclei. And as they orbit, they have a certain period. And this period can then be converted into a specific frequency that represents the certain resonance of the atom. So similarly, that a photonic resonance describe a similar phenomenon that is a photon can be trapped inside of a confined space, and then it would also trace and retrace itself around a certain orbit and also repeat itself at a certain period. And that construct a certain frequency, and that frequency is its resonant frequency. So that's a intuitive description. But in order to really make a cavity, there are quite several ways of making cavity. The simplest way is the so-called fibropolar cavity, which I'll describe momentarily. There are other ways to make cavities, such as plasmonic structures and photonic, as well as metasurfaces. But the simplest way is taking two partial reflecting mirrors and put them really, really close to each other, so that the inter-optic distance L is on the order, or is roughly equals to half integer of the wavelengths that we care about. Okay, when you do that, the photon will be trapped between these two optics and then bounce back and forth, so that the wave part of the photon would form a standing wave. And that standing wave, if it can constructively interfere with itself, that form the photonic resonance. Okay, so if we take a linear spectroscopy, usually what you see is a very sharp resonant peak, and that indicates a cavity resonance is formed, quite like actually the vibrational resonance or atomic resonance that you see. It's a very sharp line. We can measure actually the decay, basically how fast that the photon would leak out from the cavity. You would usually see a exponential decay, indicating basically the lifetime of this cavity photonic field. And this is all simulations. Okay, so a unique property of this this cavity photonic cavity mode, it has a so-called a dispersion. So specifically, one can derive this equation, basically show that this confined photon would follow a parabolic dispersion relationship, where this k parallel is the in-plane momentum. So that is basically also related to the incidence angle of the beam relative to the optical cavity normal incidence. If the beam is perpendicular to the cavity optics, then k parallel would equals to 0. So that means the cavity mode would at its energy minimum, but as the cavity the beam move more close to bigger angles, then the cavity would go to a higher energy. So by actually control this, you can also figure out what is the effective mass of the cavity mode. So it's quite similar to how people describe, other dispersion relationships in solid state physics. And that is quite different from matter, because of no matter if we're talking about atomic resonance or molecular resonance, usually the resonant frequency do not change as how we interrogate the matter materials. Okay. So then, back a while ago, physicists have already asked this question. That is, if I take an atomic resonance and a photonic resonance, and I put this atomic resonance inside of the photonic resonance or inside of my cavity, what could it be done? And what they found is that if the atomic resonance have a large enough dipole moment, then they can reach to the so-called strong coupling regime. And this regime can be described by a very simple Hamiltonian. That is, you have two diagonal diagonal elements in this block that correspond to the energy of the cavity resonance, and also the energy of here would be an atomic resonance. It could also be a vibrational resonance, where they couple to each other through this small g, and this small g is dictated by the dipole moment interactions. Okay, so this is a simple 2x2 Hamiltonian that usually I believe many schools teach in their fundamental quantum mechanics class. So if you diagonalize this Hamiltonian, that's what you will see. So you will get two new eigenstates, where that the eigenstate first take an average of the two original states in terms of energy, and then have this additional term. where this additional term is determined by this delta here, which is the energy difference between the cavity and the vibrational mode. And that is referred as detuning in polariton science. And then additionally, the coupling strength G is also involved and contribute to the separation between these two modes. And clearly, if you see if the energy of the cavity and energy of the vibrational mode equals to each other, then delta becomes zero. And as in that case, this is the so-called zero detuning. And then the energy difference between this mode and this mode is simply twice of G. And this energy separation is referred as the Rabi splitting here. And the downside of the criteria for strong coupling is simply that these Rabi splitting has to be larger than the average width of the matter and the cavity mode. Right? Or if we convert these formula here into a simple diagram to give you more intuitions, it is simply like this. So you will have a cavity mode, and then it's strongly coupled with the atomic transitions, and then when they couple to each other, they split, where the new eigenstate are referred as the upper and lower polariton. And they are, as I will show you later, they are a hybridized state as they have both the matter component and also the photon component. So this might seem similar. This is simply just diagram wide. It looks just like the molecular orbital theory that we teach our undergrad. If you have two oxygen atoms and when they couple to each other, they would also form the bonding and the anti-bonding mode that is delocalized. So it's a very similar concept, except now that we replace one of the atomic resonance with a photonic resonance. So another intuitive way to think about it is that if you take a spectrum, then the spectrum would split that single peak cavity mode into a double peak. And this double peak simply reflects the upper polariton representing the higher frequency peak, and the lower polariton that has the lower on the lower energy side. And you can easily just measure their separations in terms of frequency to determine the Rabi splitting. But what I want to also focus on or emphasize is that to look at the time domain data. So if there's a way, there's several ways, such as using ultrafast spectroscopy, you can actually follow the energy that's been put into the matter mode. Let's say that we initially excited the matter, but what you will find is that the matter would actually not hold the energy. Instead, it would decay and transfer energy to the cavity, and then the cavity also cannot hold the energy, but will transfer back to the matter. So this is really what's happening inside of the cavity. So the energy that you put to either the cavity mode or the matter mode cannot stay there by itself. Instead, they quickly exchange with each other. And this exchange rate is so fast, which is determined by the inverse of the Rabi splitting, right? So that it's so fast, it actually beats the dissipation rate of either the matter, of both the matter and the cavity. And the dissipation rate is determined by the fluid's half max. So that is why that this is the strong coupling criteria. What these frequency domain criteria is telling us is simply that the exchange rate between the matter and the cavity is much faster than the dissipation rate of both parties, so that we really cannot tell whether the energy is excited or put into the matter or the cavity mode. And we will need to use this new eigenstate that is the polaritonic mode to describe it. So the way to see it is to just write out a wave function of the polaritonic mode. And as one can see that for the upper polariton, that they are determined by a mixture of the cavity and vibrational mode, so as the lower polariton. And those two modes are orthogonal to each other, and the composition is simply decided by this cosine function, where the theta is the so-called mixing angle. So indeed, the word of polariton was coined and first recognized by John Hatfield, the guy who got Nobel Prize for neural network, he actually referred this as the polarization field particle. Analogs to photons will be called as polaritons, just as a fun fact. And importantly, once the matter form a polariton, it adopts the property of the photon. And one important manifestation is that now the polariton mode also adopt a dispersion curve just like its photon counterpart. This is the dispersion curve of the upper polariton. This is the dispersion curve of the lower polariton. And by tuning the particle along this dispersion curve, we can actually control and manipulate the composition of the polaritonic mode. For example, at zero detuning for this particular cavity, that the upper polariton has more photon component and less matter component. You have to tune it more close to here, right, around maybe 4 degrees, then the polariton mode would have a 50-50% composition of the photon and matter mode. So this is important. It means that by changing the incidence angle of how the polariton interact with a incoming light field, you can actually selectively pump the different population of polaritons along this dispersion curve and actually utilize their different properties. So those are all established concept for a long time ago, in the physics field. And it was about a decade, a little bit more than a decade ago, that chemists start to think about, okay, can this amazing strong coupling phenomenon be adopted into molecular science? Specifically, can strong coupling occur in molecular modes such as vibration or electronic transitions? However, there is a caveat here, that is, those transitions usually have much smaller transition dipole moment compared to the atomic resonance, which usually is a Rydberg, state. So the quick answer for that is yes, it indeed can reach to strong coupling. For example, two pioneer work done by the Eberson group and also Blake Simpson's group back in 2015, exactly, I guess 10 years ago, have shown that by taking some polymer molecules and put them into the cavity, indeed the vibrational mode can reach to strong coupling with the cavity mode. Okay, in both of the case, you can see there's a large Rabi splitting. So that indicates it's already in the cavity, in the strong coupling mode. And inspired by their work, my group as well took one of our favorite molecules, tungsten hexacarbonyl, and stuffed it into a cavity. This is in a hexane solution. And by taking the FTIR peak spectrum, we can also show that we can form a two polariton state that has a really large separation, nearly about 40 wave numbers, which is very much larger than either the vibrational mode with half max or its cavity resonance. So we also demonstrated that we can reach to strong coupling. However, now I need to pause a little bit because I want to give you a caution or a caveat to tell you here. That is, now instead of having this beautiful very clean picture in the atomic physics where you just have one atomic resonance to couple to the vibrational mode, we are now in a complete different regime. People refer that as a collective regime. So what is that? It is that instead of having one molecule inside of a cavity to couple to the cavity resonance, we have many molecular modes to collectively couple to this one single cavity. So you can imagine intuitively it's going to be like this. A photon is absorbed by a molecule and emitted by the molecule again, and then reabsorbed by another molecule and emitted back and forth so many times. So they collectively that reach to a strong coupling. It's kind of like, we individually may not have a lot of strength, but collectively they have a lot of strength. Okay. So that changed the physics there, and we do need to modify our Hamiltonian. And this Hamiltonian has also been already developed by Tavis and Cummings, so it's called a Tavis-Cummings model. So we modify that 2x2 Hamiltonian now into a slightly more complicated Hamiltonian, where we still have a cavity resonance energy occupied along the diagonal, but then we have many, okay, n diagonal elements all describing the vibrational transitions, where each of them are coupled to this cavity mode, and their coupling is determined by the single molecule vibrational dipole moment interaction. So this is slightly more complicated Hamiltonian to diagonalize. Nevertheless, this has already been done, and if you do that, you will find the eigenstate more or less look like this. So what you have is that there are still two eigenstates that have a energy formula just quite like the one that I showed you for the Jens-Cummings Hamiltonian, right? It is nearly the same. You have the average energy here, and you have the detuning here, and you have the G square here, except there's an N in front of it, okay? And that is the difference. So that made, now we need to modify the Rabi splitting term still equals to 2G, where this G is a collective coupling strength. But this G is actually equals to square root of N multiplied by the G naught. So the coupling strength is precisely enhanced by square root of N. So you can see the more N that you can put inside of a cavity, the more coupling strength that you have. So it's more precisely, the collective coupling strength depend on square root of N divided by capital V, where this V is the volume of the cavity mode. So what I'm telling you here is the collective coupling strength really determined by the concentration of the matter state that you have inside. And except from this difference, the second difference is there's also n-1 other eigenmode. And those eigenmode, I will tell you that they are called the dark mode, and their energy is determined to be precisely equals to the vibrational mode without experiencing any strong coupling. So that is basically the result when actually we reach to the collective strong coupling regime. And if I convert that into the energy diagram that I show, it doesn't really differ much from the Jens-Cummings Hamiltonian. We still have upper peloton and lower peloton. They are still separated by the Rabi splitting that can represent the collective coupling strength. But there is just this additional amount of dark mode. Okay, so that is the difference basically. If we move to characterize, this is the data from my own group of Thomson Hess Carbonyl, you can see that those peloton states still actually would adopt the dispersion curve. And by solving the Hamiltonian, we can show by changing the beam incidence angle, we can actually tune the composition of the upper and lower peloton, just like how people achieve that in single atom strong coupling case. And then if we solve its wave functions, you can see that the wave function is still composed by two parts. One is still the cavity parts. This composition is determined by the cosine theta, where there is a vibrational part. It's not it's not dictated or contributed by a single vibrational mode. However, here it's actually contributed collectively by all the vibrational mode involved in the strong coupling. Okay, so it's really equally shared among all of those modes. And because of this property, as you can see, I would say that peloton is a hybridized light matter quasi-particle. There is the light part, there's a matter part, okay? And then, very importantly, it is also delocalized because you see how this vibrational mode is, how this peloton mode is equally distributed among all the vibration mode involved in strong coupling. So it's really a delocalized excitation, quite like, excitonic state in some of the organic semiconductors. And then also, as obviously you can see, they have modified energy. And those are all the motivations that lead people to think they could actually influence chemical molecular properties and also chemical reactivities. Still, with one caveat, there is also the wave function of the dark mode. So this is one of the representation of the wave function of the dark mode. So you can see why it is called the dark mode now. This dark mode do not have any composition of the cavity mode. It's purely composed by the molecular parts. And indeed, it has many different representations. And theoretically, people have predicted those dark mode would have properties that is very, very similar to uncoupled molecules. Just for example, one of the property is that their energy is basically the same as uncoupled molecules. So that lead to basically the important questions in terms of mechanism, how to understand the phenomena observed in proton chemistry. That is how one can explain that basically the majority of the minority of protons, so we only have two proton mode, where the dark mode have n-1. Okay, so usually that in order to reach to strong coupling, the n that we need to use for the molecular side is on the order of 10 to the 7th to 10 to the 11th. That was at least predicted by simple theory. And so you can clearly see that, well, those protons are really minority. They have basically two states there, but there's n-1, which is on the order 10 to the 7th to 10 to 11th mode. So how would those really, really minor protonic state dictate the reactivity, while the majority of the state are still the dark mode? So this is really one of the important questions that we try to answer. And then also importantly, consider that an important thing to indicate to dictate the chemical reaction is the energy dynamics inside the molecule. We specifically want to explore and understand how protonic formation and cavity would modify or disrupt molecular energy dynamics. And in order to do that, that we really need, a technique that can differentiate a protonic state from the dark mode and be able to follow dynamics. So I may sound a little bit pessimistic, but I want to show you that there are cases where that minority can actually really dictate what happened. Especially in this case, I want to give you a positive example. That is like those people, Steve Jobs and Bill Gates, they are amazing people, but they are just minority compared to the rest of us in the world. But nevertheless, they can make a difference to the world. So maybe that's what Proton is doing, but we want to know why. So I see Yudhishna has
Yes, wait. I think this is a good point. We are half an hour into the tutorial. This is a good point for opening up questions for 5 minutes, and then you continue again smoothly.
Great.
So I request the audience, if they have any questions right now, midway, as the topic has been introduced, to ask to Wei. Are there questions? Please unmute and directly ask. Okay.
I had a question actually, if
Yes.
possible.
Yes, please.
Yeah, Wei, thanks for your talk actually. So I was looking at the Tavis Cummings model that you just put in the previous slide. So here, all the couplings of the cavity with the different vibrations are the same. I was wondering, I mean, essentially, if these couplings have like, different strengths. And let's say, for example, if your minority, if one of the couplings was, for example, dominant, in that case, how would the situation change in that case?
Really good question, Revenger. So this is a toy Hamiltonian. This is a extremely simplified case. So tomorrow, I will mostly use at least 20 minutes to explain how energy disorder and also coupling disorder would actually change the picture. So without spoil the content tomorrow, I'll basically say if indeed this coupling strength is not should not be uniform, right? because it's determined basically how the dipole oriented relative to the cavity field.
Right.
So I would have an isotropic distribution. So I can put an isotropic distribution, but what it actually dictate later is that if the dipole is perpendicular to the field, it simply do not involve in strong coupling.
Right.
Where that if it's 45, it involve, you can roughly think it involve half. So
Right.
the localization or its involvement basically change. So it's not evenly, distribute when you excite the proton. I don't think it's evenly distributed among all molecules. Some
Right.
would actually participate a little bit more, some would be slightly less.
Okay.
Right. Yeah, and then the angle of incidence dependence would also be complicated based on that.
The angle of incidence here, you mean angle of incidence of the laser?
Yeah. Yeah.
Yeah, so that has one effect that is basically dictate the cavity resonance frequency. The other would of course be actually the projection of the field into either the z-axis or x or y-axis. Yes.
Okay.
Right.
Thank
Thanks.
you. Thank you. That was Professor Ravindra Venkatramani, a faculty member in DCS. Okay, now we have Vamsi Vura, another faculty member in Department of Chemicals. Vamsi?
Hi, Bert. So I was just wondering in this two-level picture that you have, when should I worry about the coupling between the ground state of the cavity and the zero state of the atom, for example?
So the grounds, that's a really good question. So that's still a very active topic in the community to explore. I wouldn't say the ground state are modified by the coupling. To modify the ground state, you really need to reach to the so-called uh, ultra strong coupling regime, where that the excited state is you cannot ignore the rotating wave approximation term, do that approximation. So you need to include that term so that the excited state can fit back to the ground state, but we're not in this regime.
I see. Okay.
So
All right.
the coupling right now is really the coupling between the two states. It's a transition. It's not a single state. I would say that.
Okay. There are two student questions. First by Polomi.
Yeah, hello.
Yeah, Polomi. Yeah,
Yes.
speak. Yeah.
So my question is, so when inside the cavity there are thousands of molecules, so they are oriented differently, right? So you were mentioning that depending on the K perpendicular, the upper polariton and lower polariton will have different wave function patterns, like depending on the theta angle. So if I have numerous molecules with different thetas, how then it will be a simultaneous combination and it will give a one state upper polariton with the combination of all the states.
So we are talking about two angles here, I think, in your question. So one angle is the molecular orientation angle, and that you can define that relative to your cavity, where the other angle is actually the beam incidence angle. And the beam incidence angle really dictates the energy of either the photonic field or the polaritronic mode. And of course, there you can actually find the relative relationship between the beam incidence angle and the molecular orientation, but pretty much it's still the same in terms of that if your molecule and the basically the field polarization align, then they contribute the coupling stress is the strongest, but it's perpendicular, then it's less. And also when you have to um, remember that when the incidence beam actually impinge onto the cavity, it's naturally be decomposed into a perpendicular and a parallel component, and so that in that way that we only need to consider the field that is perpendicular and parallel to the cavity.
Okay. Okay.
Thank
Thank
you.
you. We have two more questions and then we will go back into the talk. So the first question is by again a student, Rijit.
Yes, I have a question that you mentioned there is the coupling of the molecular mode and the photonic cavity mode, coupling between one cavity mode and molecular mode. There is possibility of multiple coupling of the multiple cavity modes with one molecular mode.
Um, Indeed, yes. So the question is are there possibilities to couple two cavity mode with one vibrational mode? Yes, there are. I don't actually have I did not plan to talk about it, but we have published work to create some advanced cavity mode instead of this fibropore cavity to show that actually the same molecule can couple to two cavity modes simultaneously. We used the checkerboard cavity in one case, and in other case, we created sort of like a confinement, so it's kind of like a quantum dots type of photonic mode to allow and then put molecules in the same volume, and then we can show that both modes can strongly couple to the same molecules. Yeah.
Okay. Okay. Now we have, of course, Professor Vivek Tiwari joining from ISC Bangalore way. So
Hey,
Vivek.
very,
Yeah.
very good to see you. I had a quick question. So, can we say that the dark modes are also collective? Because, I'm thinking in the sense of their optical transition strength is always quite small compared to the polariton modes. Now, the reason we say they are dark is because they don't mix with the cavity mode. But the fundamental reason for that is because they are like k greater than zero kind of states where the net coupling to the cavity cancels out, so they are dark also because they are collective. So can I say that the dark modes are collective in that sense?
So I think yeah, I have been bothered by that quite a bit, but
Me too.
I'm not bothered by that anymore because realistically, if you start to include a little bit disorder into the system, you will see that the reason that I'm bothered is that the dark mode, actually you can write the dark mode wave function in many different ways. So you can call it collective, you can call it not collective, delocalized, whatever. But if you include a little bit disorder, you will quickly see that the dark mode all collapse.
Okay.
In other words, even if you prepare the dark mode delocalized in a delocalized way, it should quickly dephase because there's no driving force to keep that delocalization. The driving force for the delocalization are really just a photon.
Okay.
And then afterwards, they should just dephase quickly. It's inhomogeneous dephasing basically.
Okay. All right.
Okay.
I think it makes sense. Okay. Thank you.
Thank you, Vivek. Now the last question before we move on. Arijit, quick question. Arijit, we can't hear you. No, we can't. Okay, maybe we'll get back to you, Arijit. Let Wei continue. And then the next break, we will take it. Okay.
Okay, thank
Wei,
you.
continue. Yeah.
Thank you for all those great questions. I really enjoyed it. Okay, so now we move to the next point. I introduced the question, right? So we want to answer those questions, and we want to actually get a technique that can distinguish polariton from dark modes and also follow dynamics. So now I'm moving on to the characterization part. Specifically, the first thing that everyone does, including ourselves, is to take a linear error spectroscopy. We use everyone's favorite tool, FTIR. And when you take FTIR, I have already shown you we got this doublet peak of polaritons. So one way to think about linear spectroscopy is a little bit complicated, is that you use a pulse to excite a vibrational coherence. You let the coherence last, and then you Fourier transform it. So theoretically, you can write that as the convolution of the first order response function, where the first order response function really measure a dipole-dipole correlation, a two-point correlation point. And importantly, that by doing this, what I want to emphasize is that you get this one-dimensional spectrum, and that tells you the energy distribution of the vibrational mode or polariton mode, which I'll come back to this concept later for the 2D spectroscopy. But practically, when we actually analyze the specific IR spectrum of proton, we use a technique called transform matrix model. So those are all the important equations here. You not need to remember any of those. These are well documented, for example, in this review of modern physics paper. But importantly, these describe the transmission of the cavity mode, where depend on the transmission of your optics and reflection of your optics, the incidence angle of the beam, and the absorbance of your material, as well as the cavity thickness. Okay, so you can see the only thing that that it depend on the molecular resonance is this alpha part, which the alpha can be written in this way, where this J mu is determined by both the real and imaginary part of the dielectric function. So this is where that the molecular resonance actually kick in. As you can see, this is a simple Lorentzian functions representing the real and imaginary part of the, in this case, vibrational resonance. So what is important is this AI here that dictate the collective oscillator strength of a certain vibrational mode, where this gamma I is the full width half max of that transition. So if we set this AI equals to 0, then what you get should be this cavity mode. So that's this blue Lorentzian here, or this really light blue. If we start to increase the AI to be slightly larger, then we start to see a small dip. If we keep increasing this amplitude, then the dip become bigger, and then the separation of the peaks start to show up. If we keep increasing it more, then they separate more and more. And at a certain point, if the separation is larger than the full width half max, in this case, the average of full width half max is roughly about 10 wave number. So you can see at here we already start to reach to the strong coupling regime. Okay, so that's basically when anyone take a linear spectrum, what people use to actually characterize their spectrum. Through that, you can get several things. The first thing that you can get is, of course, the coupling strength. You can also get the detuning, because of in this way you would be able to get the length of the cavity. You'll be able to get the resonance frequency of your vibrational mode, and then the difference of the length dictate the cavity energy, right? So the difference of them indicate the detuning. Of course, you can characterize the proton by itself with half mag and so on and so forth. But clearly, as you can see from the simulation, first of all, it's not actually sensitive to the dark mode. We only see the two protonic state. The dark mode, by definition, we don't see much of it. And secondly, that of course this linear spectrum, it only contains in principle also contain all the dynamic information, because you're measuring a decoherent dynamics. However, it is just very difficult to extract it out. Okay. So then there's also a disclaimer I want to say, that is based on these analysis, as you can see, that the transform matrix model is basically a treatment of electromagnetic field as a classical. Okay, so there's no quantum involved. Where that we do actually treat the matter transitions as Lorentzian transitions, that is kind of a quantum description. So this is a semi-classical description. So what I want to say is, although previously when I introduced the concept of proton, I used the concept of cavity quantum electrodynamics, but you don't need to. You can just use classical EM to actually describe the proton here. When it actually involves quantum QED is when actually you have a quantized single photon light source and then to study single photon dynamics. So, you know, as anything, just as many, you know, Newtonian dynamics, it can also be described by quantum mechanics, but it's not necessary. Okay. So then in order to actually really try to further distinguish the dark mode or see the dark mode and polariton mode and also follow their dynamics, we move on to this technique that I learned from my grad school, that is two-dimensional infrared spectroscopy. So conceptually, if you recall from linear IR, we use one laser pulse to create one coherence. Here, the trick is that we need to use multiple pulses to create at least two vibrational coherence. The typical way that this is being done is that you use one laser pulse to create a coherence. You stop that coherence by a second pulse, and then you wait for a little bit time, that is the T2, and then you relaunch the coherence again and let the coherence to oscillate and last for a while, and then you characterize those two coherence. So it's experimentally that we do this experiment with a palm pulse, use a pulse shaper to create a double pulse that is in our palm beam, and then a probe pulse that is on the separate beam, so that they create these three pulses to excite the two coherence. And then we just let the signal to pass through the sample and then directly measure that. So importantly, that because our polariton are really sensitive to dispersion, to the implant momentum of beam incidence angle, so we want to make sure that for both the pump and probe beam that they impinge on the sample with the exact same frequency, and that is the important part. So if we do everything right, we get this type of spectrum. So I'll show you how we analyze this spectrum after a few slides. But importantly, that this 2D spectroscopy measure a third-order nonlinear response function, and it basically is the response function convoluted with these three electromagnetic field. The response function by itself measure a dipole, a 4-point dipole correlation function. But here, what is important is track actually the coherence evolution during the T1 time and T3 time. So when we Fourier transform these two coherence to get this two-dimensional spectrum, remember the 1D spectrum tells you a energy distribution of the quantum state. And here we get the energy distribution of the quantum state at two different time incidence. Therefore, we are tracking basically the energy distribution evolution or energy correlation between those quantum states. And that is the magic of the 2D spectroscopy. Or another way to think about it for those of you who are familiar with palm probe spectroscopy, when you get a two-dimensional spectroscopy, what one can do is take a horizontal cut, in our case, of the 2D spectrum. And what you get is basically a response like this. And what that tells you is basically that when I excite my pump resonance, that energy not only stay within its own resonance, it somehow also perturbed a neighboring state that causing this cross peak. And in the context of polariton, that indicates if I excite the upper polariton, the excitation not only stay in the upper polariton, it would also somehow couple to the lower polariton. There are many different coupling mechanism, which I will talk about that later. So if we apply this strategy to the real 2D spectrum of polariton, for example, if we take a horizontal cut again at the upper polariton pump region, this is the spectrum that you find. So it's a double derivative shape here. So why we see a double derivative shape? And to understand that, this is actually described by the community as Rabi splitting contraction. So I want to remind you about Rabi splitting, and we need to go back to use the transform matrix model. So importantly, that you remember the Rabi splitting or the coupling strength is proportional to the square root of concentration, specifically the number of molecule that is strongly coupled inside of the cavity. And when I perform a 2D spectroscopy, a pump probe spectroscopy, I simply would lift some of the molecule from the ground state to the excited state. It doesn't matter if it go to the proton state or dark mode. It's basically not available to be strongly coupled with the cavity anymore. As a result, this N would drop down. So in terms of the transfer matrix model, it means that this A, the amplitude of the A would decrease. As I show you here in the simulation, you can see in the transfer matrix simulation, in these two cases, if I make the A to be 90% of the original A, you can see the coupling, the Rabi splitting move inward because of the reduction of the number of molecules strongly coupled. And then if we take the difference between these two, we can reproduce qualitatively of the double derivative shape. So what this basically indicates is that as we excite the population from the ground state to the excited state, it reduce Rabi splitting. That's why it's called Rabi splitting contraction, and then make both the upper and lower proton to move inward towards to each other. So that's the first phenomenon that people usually see in when they take 2D spectroscopy of proton. There was a alternative explanation from the Scholz group before, where they explained that as a quantum transition. Basically, they considered that there is transition from the ground state to the protonic state, the one particle manifold, and then there would also be transition from the one particle protonic state to the two particle state. And their explanation is that if this is purely due to Rabi splitting, then when they run their experiment, as they let the pump probe time delay last much longer, because of those excited states should relax back to the ground state, they would expect to see the Rabi splitting to change gradually from contraction to move back towards to where they were. So they would expect to see the peak shift, the peak position shift as they actually change the time delay, and they didn't see that, so they think it's more quantum picture. So what I would like to mention is that one has to remind themselves that all the pump probe or 2D spectroscopy are still in the perturbative regime. Okay, so this is how we take actually either 2D or pump probe spectroscopy. So we basically take, the transfer matrix result spectrum, if we model it, right, at a different time delay compared to the time before the pump come in. And when it's in the perturbative regime, one can pretty much write down the differential spectrum as the first order derivative in the perturbative regime. Therefore, basically, the spectrum that we see should actually be just the derivative of the spectrum versus the amplitude of the molecular transition. And then the amplitude are simply just dictated, or the amount of first excited or ground state population removal are simply reflected by the amplitude of this derivative shape, as we show it here. So you wouldn't actually expect to see any peak shift even in the Rabi splitting contraction scenario at the perturbative regime. However, you would start to see it if you really pump it really, really high, and you are not away from, you are actually away from the perturbative regime. In that case, one start to actually consider higher order terms such as a Hessian. And this is actually a result from Adam Dunkerberger's group, where they show if they actually excite the proton, use a really high power, they can indeed see the Rabi splitting actually contract towards to each other, eventually be even away. So the Rabi splitting contraction picture still hold. So I would say that at least for all the spectral feature we show that can be explained by Rabi splitting contraction, there might be this two particle picture, but it's not necessary to get that involved. All right, so next, what I want to show is the evolution of the spectrum. So as I showed you that at a very early time, we see this Rabi splitting contraction feature, but if we keep waiting the scanning the lifetime, we see while the upper proton set are still the Rabi splitting contraction derivative feature, but the lower proton set grow in as a nearly dominated by an absorptive type of feature. And the reason for that is that as we wait for a certain time, that the proton mode start to relax back to the dark mode, where the dark mode behave just like a regular molecular state. So it also have a anharmonic 1-to-2 transition on the excited dark mode. And this transition for the tungsten Hess carbonyl, its transition happen to overlap with my lower proton window. So as it's basically as the proton relaxes population to the dark mode, this absorptive peak would start to grow. And as you can see from the transform matrix model, where we can simulate the ground state proton spectrum without any excitation, or 50% of excitation to the dark to the first excited state dark mode, you can also see a dip here. And if we take the difference, we recover this type of absorptive type of feature. So this turns out to be a really, really important feature for us to study a lot of dynamics that I will talk tomorrow, because of what these feature allow us to do is to really follow the population relaxation from the protonic state to the dark mode. And why this matter? Because the proton actually only lasts for a few picoseconds. And if you think about a chemical reaction, even for the fastest chemical reaction, is probably in the solution phase. It's gonna happen on hundreds of picosecond, nanosecond, or longer. Therefore, what really matter, we're not expecting actually the chemical reaction happen right at the protonic state. But indeed, I think what is more important is that as we excite the proton state, how it's going to manifest and really its energy into those molecular state and further change the chemical reactions there. So that's why it's important. I want to show you one example. So at an early study, when we study the proton dynamics, we use this specific state to track how the upper and lower proton relax or transfer its population to the first excited state dark mode relative to each other. So what you can see here is when we actually excite the upper proton, we see the upper proton immediately transfer its energy into the first excited state dark mode and then just relax. However, for the lower proton, we see a delayed rise and then follow decay. So our explanation is then that mass indicates that instead of direct transfer from the lower proton to the excited state dark mode, there has to be some intermediate state involved when we excite the lower proton. And then by inspecting the spectrum more carefully, we see a really, really small hump here that could correspond to the 2-to-3 transition of the dark molecular modes. And then we follow the energy, the spectral evolution as we increase the time, we see the this peak would go down, where this peak would grow back up. And if we plot its dynamics, you can see this peak would also decay, where the other peak would rise. So what we see basically is a relaxation from the second excited state and a rise from the first excited state. So we come up with this picture to propose that there are some proton-proton scatter or second excited proton interactions so that it would allow the lower proton to directly populate the second excited state of the dark mode, which further feed into the dark state of the first excited state, where that upper proton do not have such a channel and just directly relax to the first excited state. And this was further later confirmed from a simulation worker from Abe Neeson and Joe Sabani's group. But what I want to show you is that basically this is a really unique and useful way to track ultra-fast time dynamics of population relaxation between proton and dark mode. And the next, I want to bring you to the attention of an unexpected peak. So we talk about, those are the protonic peaks, and this is a cross peak between protons. We have already talked about those peaks. But there is an unexpected here. And if you look at its resonant frequency, it's right around 1980. That is where the molecular absorption is, or where my dark state is. So what it indicates is in my 2D spectrum, I not only can excite those protonic state, that is a bright state, but also the dark mode. The dark mode indeed is not so dark. And this has actually been predicted by a paper, that's 30 years ago now, where they studied how energy disorder in a solid state protonic system would manifest. What they conclude is as they keep increase the energy delocalization, energy disorder, they find that the dark mode becomes slightly bright because of the break of the symmetry. So we went ahead also test that. The way to test it is very simple. You just add a little bit disorder along the diagonal matrix. This should be G here. Sorry, I forgot to change it. But you add this disorder into your Tavis-Combin model. And once you do that, you can see as we increase the disorder, the dark mode become kind of not so dark anymore. So it show a really a big blob representing small absorption of dark mode. If we take a cut here, we can also see that we see the absorption from the dark mode. So this is just a side effect due to the fact that for any chemical system, it's never gonna be purely homogeneous. There is always energy disorder and inhomogeneity there. But it's important because that means that we now not only can track the dynamics involving proton, but also the dynamics involving dark mode. So lastly, I want to just, so that's is the second useness of 2DIR. And lastly, I want to show you that just as many of you know that with ultrafast spectroscopy, a very useful tool is the so-called anisotropy, where you can take a 2DIR pump probe spectrum with all beam parallel to each other and take another measurement with the beam, the pump and probe beam perpendicular to each other. And if you use this formula to calculate the anisotropy, what theoretically you get is basically this formula here, that it has two important terms. This P2 term, it depends on the relative angle between the mode that is involved, giving you the nonlinear signal. For example, in this 2D spectrum that I hypothetical 2D spectrum here, this cross peak indicating a cross peak between the upper proton and the lower proton, let's say. So if there's an angle between upper and lower proton, then it would manifest in this P2 term here, where this exponential term tell you the rotational diffusion dynamics, which is less relevant here, but this first term here is critically important, as I will show you later. Especially tomorrow, how we determine the origin of some of the cross-peak dynamics. So that is the second part of what I want to show you, that is the uniqueness of using 2D spectroscopy to understanding dynamics of protons. Specifically, I want to recap three important parts. That is, using 2DR spectroscopy, we can follow energy transfer or population transfer dynamics from the proton to the dark mode through that giant absorptive peak. And then second, because of the dark mode is not so dark anymore, we can actually distinguish dark mode from proton through exactly where we excite the in our experiment. And lastly, we can also measure anisotropy to determine the relative angle between different modes. So with the time, Yudhishma, I don't know how much time that I have.
Yeah, maybe we can keep the last one, the intermolecular energy transfer, for tomorrow. Will that work
Of
for you?
course.
Yeah,
Of
yeah.
course. Yeah, that is actually about application. So I want
The
to give you
application.
a teaser, but I can definitely, I'm more than happy to put it in tomorrow. It actually fit into tomorrow's topics more.
Okay, perfect, Wei. So, Wei, thank you very much for this great start to the two lecture series. I think it was fantastic. You made the questions very clear and you definitely demonstrated the importance of 2D IR. And thank you for doing this phenomenal work that's coming out from your lab and cleaning up the ideas and understanding, especially about the energy, the fast energy transfer between the bright and the dark. So, dark modes. So, I think I will open the talk for further questions, and I will like Orijit, the student
Thank
who
you.
couldn't ask the question, to go first. Orijit?
Yeah, can you hear me?
Yes.
Yeah.
Yes.
So actually, it's better that you cleared the 2D spectroscopist idea in the second half. So you talked about the dark states being used in the some kind of energy dissipation pathway as you see the evolution, right? So I was thinking about this idea. Is it is the energy dissipation pathway faster because of the presence of so many dark states when you have aggregates rather than only one molecule in cavity?
This is a perfect question. It is indeed faster. Usually it's on the order of 100 femtosecond. If it's not, sometimes it could be a little bit longer. What I will talk about is tomorrow to compare the transfer from the proton to the dark mode and a possible channel from dark mode back to the proton mode.
Okay. And another question is in 2D IR, we often see the coupling between two different modes, for example, be it vibrational or vibronic, for example. So here we see the coupling between lower polyreturn and upper one and the dark. So what about the other vibrational modes which are also present in the molecular systems?
This is great, really good question. The system that I show you today, the tungsten-Hesse carbonyl,
Yeah.
it really just have one bright
Oh, I see.
vibrational mode
Okay,
in that
okay. It's
area.
because of the symmetry. Okay.
Yeah, so
Yeah.
there's not much anything
Okay.
else.
Okay.
Tomorrow, for all the data I show you, is much more complicated. Not much more, two modes. Because
Yeah.
if you have two vibration mode, you now
Yeah,
have
yeah.
three proton
Got
mode is enough for us to analyze that, right? But the more that you have, the more complicated things would be.
Yeah, yeah, yeah. Thanks. Great.
Okay. We have our youngest faculty member, Professor Shomnath Bishash. He is here. He asked the question. Yeah, Shomnath?
Hi, can you hear me?
Yes.
Yes. Yes.
Yeah, so my question was, so in one of the figures you show that as the population transfer happens from the upper polyreturn to the lower polyreturn, you see very nice absorptive profile for the lower polyreturn states. But for the case of upper polyreturn, the line shape gets more dispersive. So can you, what can you learn from here, and can you explain that a little bit more?
Yeah, that's so I think you are asking.
Yeah, right here. Yeah,
So yeah, so
yeah.
that's a good point. It's you know the spectrum. So a short answer is we don't have quite unique. You know, we do not extract a very clear physics from this shift here. We think usually what happened is that there this change here is dictated by not only the, you know, there will be a change of the ground state population, as well as even the existence of this excited state absorption could actually contribute to that a little bit. So it could come from that. Usually what we do is when we fit the data, we use the transfer matrix model and try to basically fit every part as much as we can because they are all interrelated.
Okay, okay, all right. Thank you so much. It was a very nice talk.
Yeah.
Thank
Now, we have our one of the younger members, Professor Kalaivanan Nagarajan, who has joined and he has started this vibrational strong coupling sort of program in TIFR and DCS. So, Kalai, yeah, your question.
Hey, Wei,
Nice
thank
to
you
meet
for the nice talk. So I have a question like, so the vibration strong coupling is considered as the transient dipoles, the molecular ground state, right, which is coupling to the cavity. But once you excite a molecule, so still will they have that particular transient dipole to couple to the cavity? Are we really exciting the polytonic states?
Good question. So the polytonic state exists before photoexcitation,
Yes.
right? So when we use laser pulses to excite, we can only actually excite the system through the polariton window. So the energy is put there
Okay.
to excite the polariton. So initially, definitely the excitation is a delocalized, as I will show you tomorrow some of the data, it's a delocalized hybridized light matter quasi-particle. And then later, it may actually dephase into just a molecular, but actually it's not made, it definitely would just dephase to that. Okay. So it's a matter of how fast that would happen, and if between the polariton excitation and purely molecular excitation, if it's enough to do something, which I will show you some evidence tomorrow. Yeah, we're not when we're excited, we're at the very beginning, the excitation definitely we're exciting the protonic state. Yeah.
Okay, by changing the excitation intensity, the light intensity, can we do something? Can we prove something about this kind of phenomena? Like by exciting more molecules, to the excited state, by giving more intensity of laser, is it possible to see whether it's really happening? Like what I'm asking, still the molecule in the ground state are coupled more, or are we excite the?
Well, yes. So good question. So if we put a lot of molecule into the excited state, then it's not gonna strong couple. Right?
Yes. Yes.
Yeah. So that is actually well demonstrated by this work by Adam Dunkerberger and Jaworski. They put a lot of photon into it, and then you see how the polytonic spectrum just completely changed to the cavity spectrum.
Yes. Yeah.
Yeah. So you can actually, in that way, you can call this is a active way to switch between strong and weak coupling.
And yes. Thank you. Thank you very much.
Okay, thank you. Tubai, one student from Shan Bakchi's lab. Tubai.
Very informative talk. I have a question that what is the lifetime of these dark states? Can it be big cross peaks of this dark state with the upper polyton or lower polyton?
Good question. So the first part is about the lifetime of the dark state. The lifetime dark state is pretty much the lifetime of the pure molecular mode from what we see. In terms of tungsten hexacarbonyl, it's on the order of 160 picosecond. And sorry, I think I missed the second part of your question. Could you
So
please?
can this dark mode also appear the cross peak with the lower polyton or upper polyton?
Can this dark mode generate cross peaks?
Yes, with the lower polyton or upper polyton mode.
We try to look for that. We could not see it. Tomorrow I will explain to you why we cannot see it. The short answer is that the population transfer from the dark mode to the polariton mode are so slow. So it is not sensitive using 2DR to see it. And this is related to one of the earlier questions asking whether the polariton relaxing to dark mode is fast because of there's a lot of dark mode. The answer is yes. And then the second part of the answer for that is that whether the dark mode to polariton rate would be slow. And the answer is yes, because of there's so little of polariton, there's so much of dark mode. Yeah.
Thank you.
Okay. So I think we have come to an end, and Vivek. Okay, Professor Vivek Tiwari again. Vivek, yes, please.
Sorry, I just thought about this question. So, Wei, I was trying to understand the effect of disorder, like when you introduce disorder in the Davis-Cummings Hamiltonian. Then is it that the optical strength of the polaritons go down, and that is why I start seeing those dark states? Or is
Yeah.
it that
Yeah.
the dark states actually gain that oscillator strength because they also mix with light?
Yeah. So you have the amount of photon wave function you have, it's a constant. It's a matter of where you distribute it. In the
Yeah.
best scenario, it distribute 50-50 between the two polar atomic state. Soon as
Yeah.
that disorder start to kick in, dark mode gets photon components, and then indeed tomorrow I will show you that at certain point you cannot differentiate dark mode and polar atom mode.
Sure,
They just appear like different state, but if you look at the wave function, they are very similar.
Okay, maybe I'll ask this question tomorrow then. I'm still confused about, because they gain oscillator strength by mixing with the polar atoms, when I introduce disorder, does it, essentially I'm breaking symmetries, and
Yes.
therefore, I'm allowing these other dark state modes as well to mix with polar atoms. So that would imply that the dark states, at least at the Hamiltonian level, were collective to begin with, right? Otherwise, if they were all localized states, then
Yes.
there's no point in breaking the symmetry, and you see what I'm saying?
Yes, they are a little bit delocalized. There's a work by my colleague Joel Yunzhou's group. They
Okay.
show that the dark mode can be delocalized among two molecular states, for example,
Sure.
in the case of disorder. Yeah, so actually as disorder kick in, the polar atom and dark mode really move towards to each other in the way of polar atom become more localized and dark mode become more delocalized,
Yeah.
and then by the end, neither are very delocalized or
Sure.
localized.
Yeah. So the polar atoms are less protected by the cavity because of disorder.
Sorry?
The polar atoms are now less protected by the cavity.
Yeah.
Right.
Because of the disorder.
Yeah.
Okay.
All right.
Okay.
Thank you, Wei.
Thank you, Vivek. Thank you, everyone, for joining for the first part of the seminar and first set of the talks. Wade, it was fantastic. We will return back tomorrow exactly at the same time. This will be a Monday evening for you, and it will be a Tuesday early morning, 9:30 for us. So we hope to meet you again, and there will be more questions. Hopefully, what we can do is tomorrow we can sort of let the questions come at the end, and we will have a half an hour session of discussion, a little bit. That would be great with that 1 hour slot. So thank you, Wei, and I thank everyone for joining this morning, especially the students and our friends from other institutes, including Vivek, Naresh, Shan. Thank you.
Thank you, Wei.
Thank you.
Thank you, Jyothishman.
Thank you, Deepman.
Yeah.
Thank you, everyone, for joining. I look
Yeah.
forward tomorrow.
Yes. Thank
Bye-bye.
you. Bye.
Bye.